Hi everyone, today we are going to learn how to solve exponential equations. Before we get started, I would like you to complete this really quick warm-up. I want you to find the inverse of f of x equals 2 to the x plus 2 power plus 1. If you cannot remember how to find the inverse of an exponential function, then what I want you to do is I want you to pause the video and go back to 7.4. That set of notes describes how to find inverses. And then when you have an answer, I want you to go ahead and restart the video and we'll see how well you did. Finding inverses and the skills that we learned from finding inverses will help you to solve exponential equations today. So go ahead and pause the video and we'll see how well you did afterwards. Alright, so the first thing that we do whenever we are trying to identify an inverse is we switch our x and y values. I'm going to replace f of x with just an x, and I'm going to set it equal to 2 to the y plus 2 power plus 1. Now, in order for me to find an inverse, I need to have the base be alone. So I'm going to subtract 1 on both sides. And when I do that, I end up with x minus 1 is equal to 2 to the y plus 2 power. Now at this step, I can't subtract 2 on both sides because technically the 2 is in the exponent position. I can't divide both sides by 2 because that's not going to help us. So I'm stuck. And whenever you get stuck, we always change our form to logarithmic form or to the opposite form. So I'm going to change this to the logarithmic form. So I have log, my base is 2, so I'm going to write log base 2 of my answer, and my full answer is x minus 1. So I'm going to put into parentheses x minus 1 just to show that I am taking the log of the entire quantity. And this is going to be equal to my exponent. My exponent is y plus 2. So now what I'm going to do is I'm going to get y alone by subtracting 2 on both sides. Now be careful. Please do not combine the negative 1 and the 2. And that's because the negative 1 the logarithm is being taken of it. So therefore we don't combine those two numbers. So our answer is going to be log base 2 of x minus 1 minus 2. And that's going to be equal to, since the y value is now alone, or the y part is now alone, I'm going to rewrite that as f inverse of x. And that's how you identify the inverse of an exponential function. Now that skill of going back and forth between exponential and logarithmic will tremendously help you in this lesson as well as the next lesson. So I'm going to have you guys write down the following. Please remember that if you have b to the x power is equal to y, we can rewrite that in logarithmic form. It's going to be log, b is your base, of your answer, our answer is y, is equal to your exponent, and that is x. And that's how you go back and forth in between the forms. So you're going to want to make sure that you have this memorized, going back and forth in between the forms. You want to make sure that that is a very easy skill for you. Otherwise, you're going to have some trouble and some difficulties in this lesson as well as the next lesson. Our learning target for this lesson is for you to be able to say, I can solve exponential equations using the properties of logarithms, and I can use the Newton's law of cooling. So we have a story problem at the end. We're going to use Newton's law of cooling to solve real-world problems. We're going to actually solve that equation using both the skills that we're learning today in terms of solving exponential equations as well as Newton's law. So an exponential equation is simply an equation in which the variable expression occurs as an exponent. So we have an exponent that will have a variable in it. Very similar to the problem that we started with today. We're going to have a variable in the exponent position, and we will need to get rid of the exponent so that we can solve for our variable. Now, a property that we've already worked with so far, especially when we were working with simplifying logarithms, is that if you have two powers with the same base and they're set equal to one another, the exponents are equal to each other. So if you have b to the x equals b to the y, then that must mean that x equals y. You would set the exponents equal to one another. Or if you have 5 to the x power equals 5 to the 4th power, x has to equal 4. Your exponents would have to equal each other. Or in other words, you could say if x equals 4, then 5 to the x is equal to 5 to the 4th power. So essentially, if you have the same base raised to some exponent, let's call it x, is equal to the same base raised to the y power, then that means that you're going to set the exponents equal to each other and potentially solve. Sometimes, though, you will not be able to change both bases to be the same, and when that happens, then we're going to use our skills from our warm-up. Let's go ahead and look at our first example. Our first example is we want to solve and check. Check is a key word. Every single one of these will need to be checked. You'll need to solve and check each of these equations, and a lot of our answers will be decimals, so we'll have to round our answers to the nearest thousandth if necessary. So that's 3 decimal places. So I'm going to look at 64 and 16. And what I know about 64 and 16 is that 64 is a perfect cube and 16 is a perfect square. I know that I can rewrite 64 as 4 to the 3rd power. So what we want to do is whenever you see 2 powers whenever you see 2 power situations, our goal is to try to change each of the bases to be the same number. So I can change 64 to be 4 to the 3rd power. And I'm going to attach that x to the 3. This is going to be equal to 16, which I know is 4 squared. So I'm going to write that as 4 squared times my exponent, which is x plus 2. Or I'm sorry, which is x plus 1. So now that I've rewritten the bases and to be the same, I can now set my exponents equal to one another. So this is going to be 3x equals 2 times x plus 1. So I rewrote the bases to be the same, I set the exponents equal to one another, and now I'm going to solve for x. So I'm going to distribute 2 to each term, and I have 3x is equal to 2x plus 2. Since 3x only has x's on its side, I'm going to subtract 2x on both sides. And by doing that, I end up with x is equal to 2. So now I'm going to substitute 2 back into my original problem, and you'll probably have to use a calculator in order to check or verify your answers. So I'm going to check, is 64 to the 2nd power equal to 16 to the 2 plus 1 power? Well, 64 squared is 4,096. And 16 cubed is also 4,096. So because both of these numbers ended up equaling the same, my answer is x equals 2. It ended up working. So now let's go ahead and look at letter B. For letter B, we have 3 to the 7x minus 3 power and 9 to the 2x power. I know that 3 and 9 are related because 9 is 3 squared. So I can change this 9 to have the same base as the other side. I can change it to being 3 squared. So I'm going to write this as 3 to the 7x minus 3 power is equal to, I'm going to rewrite 9 as 3 squared, and I'm going to multiply it by 2x. Now that I have 2 powers with the same base set equal to one another, I'm going to set the exponents equal to each other. So I'm going to write this as 7x minus 3 is equal to 2 times 2x is 4x. I need to bring all of my variables to one side, and since 4x is a side that only has x's, I'm going to subtract 7x on both sides. So now the 7x's cancel out, and I'm left with negative 3 is equal to negative 3x. Dividing both sides by negative 3, I find that x is equal to 1. So now I'm going to substitute 1 back into the original problem to see if it actually works out. So here's my check. I'm going to write 3 to the 7 times 1 minus 3 power. Is that equal to the 9 to the 2 times 1 power? So 7 times 1 is 7, and 7 minus 3 is 4. So is 3 to the 4th equal to 9 squared? 3 to the 4th is 81, and 9 squared is 81, and they both equal the same number, so therefore x equals 1 is indeed a correct answer. So now I'm going to look at letter C. And letter C, we have 6x is equal to 27. And unfortunately, 6 squared is 36, and 6 to the 3rd power is 216, and 27, it's 3 to the 3rd power, and we really can't adjust it in any way so that the bases are the same. So what do? Well, I want you guys to write this down. When the bases cannot be changed to be the same, so when the bases cannot be changed to the same number, change your problem to logarithmic form. Then use the change of base formula to solve the problem. So when the bases cannot be changed to the same number, change to the logarithmic form, change your form to logarithmic form, then use the change of base formula we learned in the last lesson to solve the problem. So in this case, I'm going to change 6 to the x power equals 27 to logarithmic form using the skill that we talked about at the very beginning of the class, or very beginning of this lesson. So I'm going to rewrite this as log. My base is 6 of my answer is 27, and it's going to equal x. Voila, I've solved for x. X is alone, but now I need to figure out what that value is going to be. So now I'm going to use the change of base formula. Change of base formula means I'm going to put into my calculator log of 27 divided by log of 6, and that's going to equal x. So I'm going to put into my calculator log of 27 divided by log of 6. And when I do that, I end up with 1.839. So 1.839 is equal to x. And this is the number that I'm going to use to check. Now clearly this is an approximation, so when you plug it back in, your answer might be slightly different. It might not necessarily be exactly the number that we get. So what I mean by that is this. When we check our answer, I'm going to put in 6 to the 1.839 power. Is that equal to 27? So when you put that into your calculator, 6 raised to the 1.839 power, when you put that into your calculator, you get a number 26.9, that's about 98 if we were to round it to the nearest hundredth. So that's 26.98, and that's pretty gosh darn close to 27. So because it is so close, we're going to say that it worked. Now, if it was really far off, then that tells you that something incorrect happened. But we're going to say that our answer is approximately 1.839. Let's go ahead and look at letter D. For letter D, we need to get the base and the exponent alone first. So that's what I'm going to write down right here. We want to get the base and the exponent alone first. So that means I'm going to start off by subtracting 8 on both sides. And I have 6 times e to the 0.25 x power is equal to 12. Now I need to get the base alone, so I need to get e alone. So I'm going to divide both sides by 6. I end up with e to the 0.25 x power is equal to 2. I can't change e to become a 2 and vice versa. So therefore, I'm going to change this to logarithmic form. Now, whenever you have a base of e, that means that we're going to use ln. So I'm going to use ln, and I'm going to write the natural log of my answer, which my answer is 2, is equal to my exponent, which is 0.25x. At this point, I need to get x alone, so I'm going to divide both sides by 0.25. And now I'm going to put natural log of 2 divided by 0.25 into my calculator. So you literally put that into your calculator exactly as you see it. Let me make sure you guys can see what I entered in. Natural log of 2 divided by 0.25. And I end up with 2.773 as my answer. So that's 2.773. Now I'm going to check my answer using plugging this number back into the original. And remember that it should be pretty close. So when you check your answer, I guess I'll check right here. I'm going to write 6 times e to the 0.25 times 2.773 power. Is that plus 8, excuse me, is that equal to 20? So put that whole side into your calculator exactly as you see it. And when you do so, you end up with 20.001, and that's pretty close to 20. So because these two numbers are so close to one another, we can say for certain that 2.773 is pretty close to what x is equal to. Now for letter E and letter F, I would like you guys to please go ahead and pause the video and try these problems on your own. And when you have an answer, I want you to restart the video to verify that you did the problem correctly. Then we'll have one more problem and then we'll be finished with this lesson. Okay, so 5 and 72, they have nothing in common. So what we need to do is we need to change this form, this exponential form, to logarithmic form. So I'm going to write this as log base 5 of my answer, which is 72, equals my exponent, which is x. What's cool about this is that x is already alone. We just have to know what number it is. So we're going to use the change of base formula. Log of 72 divided by log of 5, and that's going to equal x. And when you put that into your calculator exactly as you see it, you'll find that your answer is 2.657, and that's going to be equal to x. So we're going to put that into our calculator, simply checking our answer, and I'm going to write 5 to the 2.657 power. Is that equal to 72? Well, if we put that into our calculator, we get about 71.972, and that's approximately 72. It's pretty close, and because it is so close, we're going to say that our answer for x works. And there's your answer. For letter F, we need to get the exponent alone first. So we're going to subtract 2 on both sides first. We end up with 3 times e to the 0.5x power is equal to 3. I need to get the base alone, so I'm going to divide both sides by 3, and I end up with e to the 0.5x power is equal to 1. Now I can't change e to be a 1 and vice versa, so I'm going to change it to logarithmic form using natural log. And that's because our base is e. So I'm going to write the natural log of my answer, which is 1, is equal to 0.5x. And when you divide both sides by 0.5, you find that x is equal to 0. So we're going to plug 0 back into the original problem to see if we end up getting the right answer. So when I check my answer, I'm going to write 3 times e to the 0.5 times 0 power plus 2 is equal to 5. Now, 0.5 times 0 is 0, and anything to the 0 power is 1. So this is really 3 times 1 plus 2. Is that equal to 5? Yes, 3 plus 2 does indeed equal 5. So therefore, x equals 0 is our answer. Now, sometimes it might not work out. So that's the reason why we check our answers. It is possible that it doesn't work. So always make sure that you check your answer to verify that the value that you came up with actually works. We have one more problem and then we're finished. And this problem deals with Newton's law of cooling. And this law states, so this is for Newton's law of cooling, and there's going to be a problem on your homework pertaining to Newton's law of cooling. Let me make sure that it is clear so that you guys can actually read it. Here we go. This law states that for a cooling with initial temperature of T sub 0, and that's capital T sub 0, the temperature, called capital T, after little t minutes can be modeled by T equals T sub 0 minus T sub r, whoops, sorry, here we go, T sub 0 minus T sub r times e to the negative RT power minus T sub r, where T sub r is the surrounding room temperature, or surrounding temperature, and r is the substance cooling rate. So there are a lot of variables that you'll need to know. And because I covered it up, I'm just going to rewrite the formula. It's going to be T is equal to T sub 0 minus T sub r times e to the negative RT power minus T sub r. I'm sorry, plus T sub r, excuse me. Plus T sub r. All right. So now what we want to do is we're going to look at this hot chocolate problem. It says the hot chocolate has been heated to 90 degrees Celsius. And it has been heated to. So if it's been heated to, that means that its starting temperature. So its starting temperature is T sub 0. So its initial temperature is T sub 0. And we're going to say that that's 90 degrees Celsius. So hot chocolate has been heated to 90 degrees Celsius and is poured into a mug and placed on a table in a room with a temperature of 20 degrees Celsius. So its surrounding temperature, so the room that it's in, has a temperature of 20 degrees Celsius. Now the surrounding temperature is your room temperature. So we're going to say that T sub r is equal to 20 degrees Celsius. If r is equal to 0.145, so we have little r is equal to 0.145, when the time t is measured in minutes, which I don't know what that is quite yet, how long, so I want to find that time, the little t time, will it take for the hot chocolate to cool to a temperature of 30 degrees Celsius. So we want the temperature to become 30 degrees Celsius. So we want regular T to be 30 degrees Celsius. And we're going to round our answer to the nearest minute. Okay, so we want to plug all of these values into our formula. So T represents the temperature that the hot chocolate cools to, and that is 30 degrees Celsius. It's going to be equal to our initial temperature, which is 90 degrees Celsius, minus our room temperature, which is 20 degrees Celsius, times e to the negative 0.145 times little t power, plus T sub r, which is our room temperature. So all I did was I took all of my information and I plugged it into the formula. So you'll need to make sure that you recognize what represents the initial temperature versus room temperature, etc., etc. So now our goal is to solve for little t. So what we want to do is we want to get the e alone, get the base alone, and once we have that base alone, we can rewrite the problem in logarithmic form and help us to find what t is. So I'm going to start off by subtracting 20 on both sides. So I'm going to write right here that my goal is to get e alone, which is my base. So I'm going to subtract 20 on both sides. And when I do that, I end up with 10 is equal to, and I can combine 90 and 20 to make that 70 times e to the negative 0.145 times t power. So once again, I need to get e alone, so I'm going to get rid of this multiplication of 70 by dividing both sides by 70. And I end up with 1/7 is equal to e raised to the 0.145 times t power. Now I cannot change 1/7 to become an E and vice versa. So what I'm going to do is I'm going to change this to natural log form, so logarithmic form. So I'm going to rewrite this as the natural log, which means log base E, of my answer, so that's going to be 1/7, equals my exponent, which is negative 0.145 times t. So now what I'm going to do is I'm going to divide both sides by 0.145, negative 0.145, and I'm going to put this expression into my calculator exactly as I see it. So be careful, make sure that you use your parentheses. I'm going to enter in natural log. Hopefully you can see this. Hold on. Natural log of 1/7, so 1 divided by 7, close my parentheses, divided by negative 0.145, and I'm going to press enter. And I end up with approximately, rounding it to the nearest minute, our nearest minute is going to be 13 minutes. So our time is going to be 13. So after 13 minutes, the hot chocolate will cool to 30 degrees Celsius. That's supposed to be a no. And that is your answer. As well as the end of today's lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.